Okay, folks, a little sorry that there's going to be some ambient noise in the video this time. I am not at home, nor am I in my classroom, but I'm working where I can to make sure that you get the materials that you need. Ultimately, we're doing a video that is on curvature. Okay, so we have the idea of curvature. Basically, what a curvature is that if I look at something that is curving, I want to know how fast is that curve turning as I move along its length. And usually what we want to do is we want to compare this to a circle. And if I have a circle of a certain radius, then it's turning at a certain rate along its length. If I make the circle smaller, it's turning faster. If I make the circle larger, it's turning slower. So if I have some space curve r of t, I want to know, like, at this point, I'm turning as though I were on a curve or on a circle that has a radius of size alpha. Okay, so curvature, though, we want to be kind of in this really interesting place. So we want curvature to be increasing as the radius is decreasing. So we're actually going to set curvature, instead of equal to alpha, we're going to make it, indirectly proportional to alpha. So we want curvature to be 1 over alpha. Okay, so we're asking, how fast is the curve changing with respect to arc length? So we're going to do some pretty in-depth construction here intellectually, so hang in with us, and we're going to show that we get a formula and that formula works. Okay, so like conceptually, we've got this idea of changing direction with respect to arc length. So in our construct here, we're going to let x be the arc length, and that's going to be determined the same way we did in our last set of notes, right? So that's not a mystery, okay? Usually we're going to define direction using this unit directional vector. So literally, curvature is the magnitude, the magnitude of the change in the directional vector with respect to the arc length. Okay, so this is the definition that we're going to use for curvature. However, the problem that we have here is that this is not very computational. So we have to decompose this a bit. Okay, so we can decompose this using a version of the chain rule, right? So if I look at this, I know that dt with respect to time is going to be dt with respect to arc length times the change in arc length with respect to time, which means that I can flip this around a bit and say the change in the directional vector with respect to arc length is going to be the change in the directional vector with respect to time over the change in arc length with respect to time, and that is something that is quantifiable. So I'm going to say that curvature is ultimately, now this is curvature now with, in terms of t, can be done dt over ds dt. Okay, and then take magnitude of that. But note, if I look at ds dt, right, this should be, see, this is arc length, right? So if I use the fundamental theorem of calculus, I get the following result, that this is the same as d dt of the indefinite integral of the magnitude of r prime of t dt, right? So that's arc length with respect to t should now give me the magnitude of just r prime of t. Aha, that's kind of nice, because that taking the derivative and that integral undo each other gives me that nice, neat little computation with respect to t. So we've simplified the ds dt part of this. We've got the denominator there down to that guy. So we're getting into a more computational definition of the derivative, or not the derivative of curvature, which is ultimately now, well, if I look at the top, that is actually the magnitude of the directional, the unit directional vector with respect to t over the magnitude of r prime of t. This can be computed. Okay, so now I have a way to find, given t, the curvature of everything. So we're in good space there. So a logical question is this computational method valid? Okay, so we got that k of t is the unit directional vector with respect to t over r prime of t. So if I apply this to a circle that has radius alpha, so let's make that r of t is alpha cosine t I plus alpha sine t j. Alright, so that'll give me a circle with radius alpha. Then r prime of t becomes negative alpha sine t I plus alpha cosine t j. Right, the magnitude of this now becomes, let's see, that's the square root of alpha squared sine squared t plus alpha squared cosine squared t, and that's just going to be square root of alpha squared, which is alpha. Okay, so that's nice. Okay, so these are alphas, not a's, but we get the point. The t vector is r prime of t over r prime of t magnitude, right? So this should be ultimately the whole thing just with the alpha stripped away. So that's going to be sine ti plus cosine tj, right? So that's my unit vector. But the nice thing about this is if I take the magnitude of that guy, right? Let's see. Well, we got to take its the magnitude of its derivative, right? So we take the derivative of that, and I'm back to negative. So the magnitude of negative cosine t I plus. Nope, that one's not plus. Minus sine tj, right? So that should come out as square root of cosine squared plus sine squared, which is of course 1. So make a little bit of room up here. That means curvature of t is t prime over r prime magnitude, which is 1 over alpha, which is exactly what we wanted. Right, so validity holds. The measure here appears to be valid, so we're going to keep moving forward here a bit. This measurement is still a little bit clunky. One of the things that we notice here is that the t is able to be computed from the r, so we should be able to build the entire formula for curvature from just the r function. Alright, so let's build curvature. We're going to have a theorem here that's going to state that curvature of t is ultimately going to be magnitude of r prime of t cross magnitude, or r double prime of t all over r prime of t cubed. Now that seems like a bit of a stretch, that we're dragging in the cross product here and somehow we're getting a cube in the bottom But I think with a little bit of work, we can come up with proof here. So let's try to prove this. T is r prime over magnitude r prime. That's just by the definition of the unit tangent vector. If I use fundamental theorem of calculus, we've shown that r prime magnitude is the same as change in arc length with respect to t. So this together should imply that magnitude of r prime is magnitude of r prime times t, which is, or just r prime, no magnitude on that one. It's just ds dt times t, which now, if I take the second derivative of this, I get second derivative with respect to s over dt squared times big T, plus ds over dt times t prime. So that's taking this, applying the product rule, and getting the second derivative. But note, big note, that t cross t, any vector cross itself, lends me to the zero vector. So that's going to become kind of critical in steps to come here. Okay, so the numerator over in this thing has an r prime cross r double prime. Alright, so that's going to give me ds dt times t cross the second derivative, right? So that's the d2s dts squared times t plus ds dt t prime, right? So a little bit of kind of manipulating things around here a little bit. You're going to get this times this, so that's going to be ds dt of d2s dt squared, and then we get the t cross t. Aha, so that's going to be helpful. And then we get two of these, so we got ds dt squared, and then t times, so this is going to be t cross t prime. Okay, so this is the zero vector. So when I'm adding the zero vector to something, it all washes out and just lets me have ds dt squared times t cross t prime. Okay, so that's simplified quite nicely. If I take a magnitude here of both sides, I get the magnitude of r prime cross r double prime is, so this is a scalar, ds dt squared times the magnitude of t cross t prime. Okay, we're going to throw a lemma in this, and we're going to ask for this lemma to exist, which means we're going to throw this in, and then later on we're going to prove it. We're going to say that if the magnitude of a vector is a constant for all t, then the derivative of that vector is perpendicular to the vector itself for all t. Okay, so that's kind of something we're asking you to swallow for a moment, and we're going to combine this with the law of sines, and we're going to make progress on our proof. Okay, so from law of sines, we get that the magnitude of r prime cross r double prime is the same as, so this is what we had, ds d squared times t cross t prime, right? But ultimately, law of sines is going to make that ds dt squared times t times magnitude of t prime times sine theta, which is the angle between them. But if we give the lemma, then we know that t and t prime are perpendicular, which forces this to be ds dt squared t prime times sine of pi over 2, because that's perpendicularity, which means that this is going to go to 1. So we get ds dt squared times mag t times magnitude t prime. Okay, but note t is a unit vector. So that means that this guy is also 1. So that's going to give me ds dt 2 times magnitude of t prime. Okay, so this is going to imply that t prime is ultimately r prime cross r double prime over ds dt squared. But we know that ds dt from earlier work is able to be simplified, so that's going to be r prime cross r double prime over r prime squared, right? That's from fundamental theorem of calculus, which we're almost at the last step here. Okay, so a minute ago we left this off at t prime, magnitude is r prime cross r double prime over r prime squared. And applying that to curvature, right? So remember, curvature is t prime over r prime, which if this is t prime, this means I'm going to get r prime cross r double prime over r prime now cubed, because you get 2 from here and 1 from there. Okay, so that proves our theorem. What we have to do is that we have to deal with the lemma, right? It's still hanging out there, so we have to take a minute to prove that lemma, and once we have that, the theorem is good. Okay, so proving this lemma is not so bad. We want to show that if the vector itself is equal to a constant for all t, then it has to be perpendicular to its own derivative. So let's try this. We're going to try v dot t dot v dot t is going to give me magnitude of v t squared, which if this thing is equal to c will equal c squared for all t. Alright, so that's fantastic. If I take the derivative of this, so I'm going to take the derivative of v t dot v t, that should come up as, let's see, that should come up as first, right, times the derivative of the second plus second, right, times derivative of the first, which gives me 2 times vt dot vt, right? This one's v prime, right? 2 times v prime times vt, because the commutative property holds here for the dot product. Now, if I take the derivative, this should be with respect to t, the derivative with respect to t of c squared, I get 0, which means that 2 times v prime t dot vt is equal to 0. Divide by sides by 2, I get v prime t dot vt is equal to 0, which means that v prime t has to be perpendicular or orthogonal to vt. So that's proof of lemma. Alright, so all we have left is to use an example of curvature and we'll be good. Okay, so let's try to find the curvature of r of t, which is t squared t cubed at the point 0, 0, 0, right? So it's not hard to see that this occurs when t is equal to 0. R prime of t here would be 1, 2t, 3t squared, and which means that r prime of 0 is going to be 1, 0, 0. Our double prime of t here will be 0, 2, 6t, which means our double prime of 0 is 0, 2, 0. Okay, so that means the magnitude of r prime of 0 cross r double prime of 0 is going to be, let's see, that's going to be 1, 0, 0 cross 0, 2, 0. And if you do a little bit of computation there, that works out to be 0, 0, 2. Okay, so that's my numerator is 0, 0, 2. To take the magnitude of that, I just get 2. The denominator here is going to be r prime of 0 cubed, right? So r prime of 0 is 1, 0, 0, so that's going to be 1 is its magnitude, cubed is just 1. So that means the curvature at time 0 is 2 over 1 or 2, which means that this has the same curvature as a circle whose radius is 1 over 2 or 1/2 units. So that's it. Once you have the theorem in place, the computation isn't so bad. You can probably propel this a little bit faster using MATLAB. Sorry about the long set of notes, but there's a lot of technical stuff that gets you to the computational formula. So thank you.